our familiar molecule, and that is H2CO3 or bicarbonic acid. As I said, bicarbonic acid can easily dissociate to CO2 and H2O acid. This is our acid. And this is our base. Acid and our base. Well, let's see what happens if we add hydrogen to our blood. For example, what happens when you use cola, you use tomato juice, or something like those foods.
The acid divide.
H add to the equation, and the equation move to the left side, so that H join to connect to HCO3, therefore produce these two things, H joint and joint to HCO3 and produce H2CO3, our acid. On the other hand, we know that H2CO3 easily or simultaneously produce H2 water and CO2. So, when we use some acidic food like cola, like tomato juice, this acidic food add a great amount of H to our body. We have these molecules in our body that combat, fight to the added acid to our body, so that the H plus that added to our body neutralized with the base which existed in our blood and produce H2CO3. On the other hand, H2CO3 produce CO2 and H2O. We know that CO2 is a gas. How can we do with CO2? With ventilation. We named it ventilation. I think in Arabic it means tahmiya. With ventilation, you remove CO2 from your body. CO2 escape from your body. You understand?
Yes.
On the other hand, when acid removes from your body, you lose acid. You lose H plus in your body. When? Whenever you use a basic food, basic diet, you lose your H plus. Another example. When you encounter with nausea, with Arabic, you named it. استفراغ. I learned Arabic in this class. Alhamdulillah. And when you lose your acid through istifrag or nausea, you lose H plus. As I said to you, your gastric juice is full of HCl, and when you lose it, you lose your H plus. So, when you lose acid, what happened to this equation? What happened to the equation? As you can see, when you lose H plus, the equation moves to the right side, so that H2CO2 dissociate to H plus and HCO3 to compensate the removed H plus. So when the body or blood lose its H plus, the equation move to the right side to compensate the incline in H plus. So, with this action, you correct the fault. You correct the error. On the other hand, when the H2CO3 separate to its molecules, H2O and CO2 need to produce this molecule. So we need CO2. How can we remain CO2 in our body? With decrease in ventilation. So when you decrease your ventilation, you remain the CO2 in your body. On the other hand, when you increase your ventilation, you lose CO2 in your body. Do you understand? Nobody?
Yes.
Very good. So, this molecule and its conjugated base is a very unique and symbolic type of buffers in our body. Buffers are solutions. Buffers are solutions contain an acid, of course weak acid, and its conjugated base. Acid conjugated base. So we have a buffer which fight against pH change, which fights against pH change in our body. So buffers are solutions that fight, in Arabic, مقاومة against pH changes. So when pH changes in our blood, in our body, in our cells, we have some buffers that don't let to pH to change in our blood, in our cells. Do you understand? So buffers contains an acid, a weak acid, and its conjugated base. Well, this is a very important graph in this slide. As you can see here, this is the pH in our solution, and that is the molecules like NaOH we added to this solution. And our solution contains a buffer. Our buffer is weak acid CH3COOH plus its base, conjugated base, CH3COO minus. Well, as you can see, when we add OH to this solution, at the first step, the pH will change very fast. As you can see here, when we add lower than 0.1 mole of OH, the acidity changes rapidly and increase from 1 to 2. Also, again, when we add some other molecules, the acidity increase from 2 to 3. Again, from 3 to 4. But we have a steady state between around 0.1 to 0.9. There is no change between this range. And change in pH is undeniable. Sorry, is deniable in Arabic. You can ده بيجي أو عربي بيجي لفظ. You can see that the change in pH is too low, but in this step the change was very high. What happened in this range? What happened to the molecule? What happened to the solution?
We add OH.
As you can see, in this region, our buffer completely resists to the changes in pH. You cannot see such resistance in other regions. You can just see these properties in a unique region. What is this unique region? We name this region as buffering region, which means the region that buffer has the highest buffering properties in a solution, and that is equal to pK plus minus 1, which means that it is a unique amount for any buffer. For example, if I said that pK is a constant, ثابت, as a constant amount for any equation, pK is a constant amount for any equation. For example, for such equation, the pK is around, I think, 5. So, the buffering region for this equation is about 5 plus minus 1. It means in pH 4 to 6, we have no changes or small changes in the pH of our solution, and that is buffering region. You have any questions? You understand?
6 minus 4 or opposite?
5 plus minus 1, or from pH 4 to pH 6, we have the highest buffering activity.
Can you explain?
Again, for any buffer, do you need to more explanation about buffers?
Yes.
Well, buffers are molecules of solution contains an acid, a weak acid, and a base. Acid, base, which resist against changes in pH. When we add acid or base to our blood, buffer resists to changes from this solution. So this is the definition of buffer. Each buffer has a very unique property, that is buffering region, which means the region which a buffer has the highest resistance against changes in pH. Highest resistance against changes in pH. For example, as you can see here, we have no change or small change. pH just changed from 4 to 5, from 4 to 6 in this region. On the other hand, pH changes in this region as more higher. For example, you can see that pH changes from 1 to 4, more than 4 units. But here, you have just 2 unit changes in pH in buffering region. So, in buffering region, you have the lowest changes in pH, and you see the highest power of a buffer in this region. What is the exact amount of buffering region? You can definitely determine this amount using this equation. The buffering region is pK of that buffer plus minus 1. For example, this buffer, in this buffer, pK is equal to 4.76. So that the buffering region is about 3.76
Or 5.
to 5.76, and that is the buffering region for this buffer. You understand?
How we know the highest buffer rate?
You mean that how we can find the buffering region? As
The number of the buffer region.
that is the highest buffering region is the highest power, highest.
How we know it's 5? It's not 6, it's not 4.
It is determined previously using experimental assessment. In laboratories, you have found that what is the pK for For example, H2CO3 and the other molecules. So that is the determined amount for any equation. You know it using experiment, using some type of assessment, laboratory assessment. So you know what is the pK amount for any buffer, for any chemical molecules. That is determined previously. So you can you should only find that what is the pK for that molecule that you need. For example, for this molecule, the pK is 4.76. So this is the buffer region.
The number one is the delta pH in this buffer region.
Well,
pH2 minus pH1 score 1 4.76 يعني 5.76 minus 4.76.
No. I wrote this equation for you. Okay. This equation shows you that a unit pK. For example, for this equation, if pK is about 5, so you should expect that the buffering region for this molecule should be 5 minus 1 and 5 plus 1, which means 4 to 6. So this is a range. This is a range. You have a question. What happened at the pK point? What is the amount of acid and base in this point, in this amount? What happened is, as you can see in this slide, in this amount, the center of this diagram, the pH is equal to pK, or 4.76, and the amount, the concentration of acid and base is equal to each other. So, at the center of this diagram, which is equal to the pK, the pH and pK is the same, are the same, and the concentration of acid and base also is equal. We have a very important equation you can see here in this slide, and that is Henderson-Hasselbalch equation. You use this equation, you apply this equation to determine pH or pK for acid concentration or water. You don't need to this part of this slide. You should only learn this equation, which is Henderson-Hasselbalch equation. pH equals to pKa plus low proton acceptor and proton donor. Well, let's continue our class with a very good example. Comparison of buffered and unbuffered solution. What happened? What is the difference between buffer solution and unbuffered solution? Well, please don't look at your slides, and if you can, solve this equation. Solve this. We have two bottles. The first one includes 100 ml of pure water, and the pH is 7. On the other hand, you have 100 milliliter of a buffer contain 10 millimole HA, which means acid, and 10 millimole A minus, which means base. This is our base, this is our acid. The pK is 7 and the pH is 7. Henderson-Hasselbalch equation is you can write it again. Sorry. Well, we add to each bottle 1 millimole of solid NaOH. If anyone can, please come and solve this equation. What happened? What is the changes of pH for any of this bottle? According to this equation, you can use this equation. Come and solve it. You should give me two amounts. What is the amount of pH after adding 1 millimole NaOH to this bottle, and what happened to this bottle?
Okay.
What is pH 1? What happened to pH for this bottle?
ايوه عاوزين
لازم.
بعدين نطلع بيش بعد
شو
الغرفه السادس متعاونين نقدر
والله القاعدة مكتوبة قدامك بس
القاعدة قدامك شوف